Classic 3D rendering assumes the image plane is a flat 2D rectangle. So in order to create the images for the VR headset, the image needs to be distorted. With a large field of view, this would result in wasteful computations in the outer screen areas. The Oculus Quest supports fixed foveated rendering, or FFR, which allows us to save pixel shader computations and memory bandwidth in those areas. Fixed foveation has 4 different quality methods available to developers. These can be set using the following blueprint node. Set fixed foveated rendering level. The higher the FFR level, the better performance savings, but at the expense of peripheral resolution. The only exception is FFR high top, which has more detail towards the bottom of the screen and more foveation near the top. With fixed foveated rendering enabled, you can notice lower resolution rendering in sections further away from the center of the image. You might see more pronounced dithering because of the lower resolution. A regular high-frequency dither pattern might even disappear. Because there is no blending between the quality levels, this might be perceived even worse than not using dithering at all. This is why we generally want to avoid dithering with FFR. FFR is compatible with MSAA, so as long as we avoid per pixel adjustments or dithering, you can get multiple shades. For more information on this, visit the link below this video. Another great optimization for the Quest is the multi-view render feature. In Course 1, we briefly discussed a render feature called instant stereo rendering. Multi-view is an optimization that improves this even further. Note, as mentioned in Course 1, we will want to make sure mobile HDR is disabled in order for mobile multi-view to work. Under rendering, mobile HDR is disabled. Here's VR. It's mobile multi-view that we want to enable. And actually, mobile multi-view direct should also be enabled. Additionally, particles are another area we need to consider when rendering for VR. Overdraw is a problem that occurs when the GPU needs to do many calculations because of the overlapping transparent sprites. Particle systems like smoke can quickly reduce performance in VR. Where possible, consider using more material effects and a few layered particle effects. Another issue with particles in VR is their inherent shape. Standard sprites are arranged to be constantly flat against your perspective. Because we are viewing the scene in stereo, it's easier for users to notice that particle sprites are flat. Avoid rendering large sprites close to the camera or intersecting the camera. It's best to use smaller particles where possible because they are easy for the eye to resolve in 3D. Particle emitters that spawn particles in a volume read particularly well too, since there is depth between particles. And there you have it. You now know what to consider when setting up graphics and rendering in your VR application. Don't forget to practice the skill you learned throughout this course and find balancing points between performance and visual acuity. In the next course, Kevin Lyle will be taking a look at how to implement locomotion into our apps.